Let's take a look at the setup of this problem. So in this problem, we're imagining a model of the hydrogen atom where the electron orbits around the proton. So here's my proton, here's my electron, and the electron is going in a circular orbit around the proton, okay? And we're told the size of the orbit. We're told the size of the orbit is 0.053 nanometers. We're told that. And we're asked this, how many revolutions per second does the electron make? Well, let's think about this. The electron's negatively charged, the proton's positively charged. We know there'll be an attractive force between those two. And in fact, that's exactly what we need. If you want a particle to go into a circular orbit, there has to be a force directed towards the center of the circle. Now, the proton is significantly more massive than the electron, so let's assume that the proton's stationary. The forces between these two are equal and opposite, but from the point of view of the proton, that's not going to make very much acceleration. But for the electron, it's a significant acceleration, and it makes the electron go in a circular orbit. So what must be true for a force that causes circular motion? It must be a force directed towards the center of the circle. What is physically the force that produces the centripetal acceleration? Answer: it's the electrostatic force between the electron and the proton. And we know that's just equal to our electrostatic constant K times the magnitude of the first charge times the magnitude of the second charge divided by the square of the distance between them. Now, the charge on an electron is just E. The charge on a proton is just E. So if I'm just concerned about the magnitude of the two forces, or the magnitude of the two charges, it's just E. So the force between the two is K times E squared divided by R squared. That's the attractive force between the proton and the electron. And that is the force that produces the circular motion. Now, we saw back in chapter 6 that to make a particle go in a circular orbit requires a force of m times v squared divided by r. So we can equate the force necessary to produce circular motion to the electrostatic force between the two particles, because that is the force that is producing the circular motion. So this is our basic working equation. And with this in hand, we're ready to proceed to a solution. So let's go ahead and solve. But before we do that, I want to think about what our answers might look like. We expect the speed to be very, very high, and the particle is going in a very, very small circle. So I expect the frequency, i.e. the revolutions per second, to be quite high indeed. Now, when we're solving for this, I'm going to start by doing this. I'm going to try to solve for the period of the motion. And if a particle is going in a circle, the time that it takes to complete one orbit is just 2 pi r divided by v. And I can solve for v, the speed at which the particle makes the orbit, by solving this relationship. If I rewrite it, I can solve for v. I can cancel a factor of r. I can bring the m over here and end up with this. V is equal to the square root of k times e squared divided by m times r. Now, all of these quantities are known. This is our constant k. It's 9 times 10 to the 9th. This is the charge on the electron, 1.6 times 10 to the negative 19th. This is the mass of the electron, 9.1 times 10 to the minus 34th kilograms. And then we have our radius. Our radius is 0.053 nanometers, or 0.053 times 10 to the minus 9th meters. So I know K, I know E, I know M, I know R. I can put in all of these numbers, and if I do that, I calculate a speed of 2.19 times 10 to the 6th meters per second. Now notice, I've kept an extra significant figure. This is a 2 significant figure problem, but I've kept a third one because this is an intermediate stage, because I don't want the velocity. What I want is the period and then fundamentally the frequency. Well, if I know the speed and I know the radius of the orbit, which I do, it's 0.053 times 10 to the minus 9th meters, I can calculate the period. And if I do that, here's what I get. Period, 2 pi r divided by v. I know r, I know v, and I calculate a period of 1.52 times 10 to minus 16th seconds. And then I can calculate the frequency. The frequency is just 1 over the period. So I just take this number and I invert it. And what I get for the frequency is 6.6 times 10 to the 15th cycles per second, or revolutions per second, because that's what we're asked for. 6.6 times 10 to the 15th revolutions per second. Now, how are we going to assess this result? We said that we expect a very, very high speed. And so at a very, very high speed in a small circle, we expect a very, very high frequency. And in fact, that's what we get. So that makes sense. This frequency is a little bit bigger than the frequency of visible light. And that makes some sense as well. And so our net assessment is we end up with a high frequency, just like we expected. It's comparable to the frequencies of visible light. That seems reasonable as well. And so our answer matches the way we understand that the world works.